name is Traynor. I'm a fourth year student in GMIT, and this video is going to take you through the thesis carried out for a Bachelor's in Honours Energy Engineering degree. The overall title of the thesis is a feasibility study for the use of CHP in a hospital. The overall aim of the thesis is to determine if the hospital is suitable for the use of CHP. To do this, there will be an analysis done on the hospital's historical energy demand. An appropriate plant will then be selected based on the results from this analysis, and then a calculation of the cost savings that can be achieved while using the selected CHP unit. The main drivers for the project are rising fuel costs. Fuels have been on the increase for the last number of years, rising the bills in the hospital, increasing energy demand at the hospital, put in a new building in 2010. Since then they've seen an increase in the amount of energy consumed. Global warming is an international problem at the moment, and something must be done to more efficiently use the fuel sources that we have left. And the hospital is searching for an overall better solution to meet their energy demands. In this thesis, a literature review was carried out. In it, the main topics: principles of CHP, the advantages of using a cogeneration system, all different types of CHP that are available on the market, and the methods of sizing a CHP, the selection, how to select the appropriate CHP plant, and then a detailed case study. Now, the methodology for sizing. The first step is to select a time base in which your CHP system will be operating. To do this, we have our time base is from 8 o'clock in the morning to 11 o'clock at night. This is to coincide with the electrical day tariff from the electricity supplier. This is because at night electricity can be bought from the grid at a cheap rate, and therefore the economic advantages of using a CHP no longer exist, as the electricity is bought cheaper from the grid at night. So the CHP system will only be operated during the day. Then you must analyse the energy demand. To do this, we will be looking at their average demand, peak demand and base demand, as the system will be sized to operate at one of these demands. The building's heat to power ratio is one of the most technical aspects used to select a CHP, and of course the cost the hospital are paying for their energy using the conventional system of a boiler and the electricity bought from the grid. Now, one's next step is to determine the operation regime of the hospital, which demand it will be sized to satisfy, and then select the appropriate plant. Now, these are the electrical demands of the hospital. So we can say here are the day electrical units of the hospital. From this study, we determined that the base load, the base demand for the electricity is 240 kilowatts, peak demand 290, average demand 265, and a total demand throughout the year of 1.4 gigawatt hours. The daytime demand makes up 75% of the overall electrical demand, so sizing the system to the day demand will mean that a large portion of the electricity is provided. Analysis of the heating demand. Now, the heating demand was actually only given to us in a month period, so there was no breaking down between day and night. So to do this, we had to estimate the consumption of gas for both day and night periods. To do this, the outside temperatures were determined at the hospital, and from the results we can see that there's little correlation between the temperatures between 8 o'clock and 11 o'clock at night, and from 11 o'clock to 8 o'clock in the morning there is little correlation, meaning that the external heating factors will make a little difference on the consumption. So the difference in consumption in day and night will be down to the processes that are going on in the hospital. During the day, hospitals' patients are bathing, theatres are operation, and the daytime staff occupy the building, so there's a large demand on the heating. At night, staff is reduced. The building has a large amount of concrete in it with a high thermal mass, so energy is stored during the day and released at night. This will lower the consumption of gas needed during the night. So with all these figures analysed and everything, and talking with the on-site facility manager of the hospital, we determined that the heating demand would be estimated to reduce by 35% compared to the daytime consumption. So from this, we have a breakdown of our day and night. Again, the day units took up about 75% of the hospital's demand, heating demand. From the analysis of the demand, we can see that the average demand was 431 kilowatts, peak demand 636, base demand was 381, the total demand of 2.8 gigawatt hours throughout the year. Here we can see the hospital demand. You can see that there is a large seasonal effect from the weather on the heating demand itself. Now moving on to the heat to the power ratio, as mentioned earlier, this is one of the most important technical parameters which will be used to select the CHP. As you can see here, we have a quite uniform electrical demand throughout the year, with heating demand that has seasonal components. Due to this reason, the heat to power ratio will vary throughout the year. We can see it's at its max here in February and December, where there's a high heating demand and the lower electrical demand, which is a heat to power ratio of 2.42. The lowest occurs in August, when the heating demand is low due to the weather, and the electrical demand gives us a heat to power ratio of 1.36. This gives us an average heat to power ratio throughout the year of about 1.9. This slide we're going to look at the energy costs associated with running the ENERG 230, which is sized for the base demand. Here we can see the fuel input for the CHP, 3.6 gigawatt hours for the whole year. This is what the boiler inputted previously. Now the fuel costs inputted into the CHP amount to €160,000. The total cost with all associated charges such as maintenance, the operation costs, the standby charge associated with CHP amounts to €260,000 for the year. Previously the hospital were paying just €320,000. This excludes any charges related to the electricity, such as capacities charges, duos and choose charges, which are set out by the electrical provider. So there's annual savings using this system calculated at just under €60,000 a year. Again, this is from analysing the system. This is all different parameters that the system produces, and we can see here the payback, the cost of each system. This is blocked, but this system costs €260,000 to install and buy. This just highlights some of the different parameters: the value of heat generated, value of electricity generated. As we can see, the value of electricity generated is here, and it's generated at just under 8 cents, which is lower than what purchased off the grid. So the system will be viable to install. Now moving on to the next, we can see here the carbon emission saves just over 2.96 tonnes of CO2 annually. Again, this is how we calculate the annual savings. Here is all the costs related, energy costs related to the electrical consumption and the fuel consumption. It's broken down into day and night periods, the hours associated with each. We can see the price of each unit is used to calculate how much the electricity costs for each period and night period. Down to fuel, boiler efficiency, dividing this by the fuel consumption tells us our heating demand, the average heat to power ratio for each period. Now underneath this is our CHP generation. Again, our electrical output, heat put. Multiplying this by our hours will give us how much is produced in each period. All costs related to running our CHP. We have our maintenance cost and our price cost. We have the cost of our shortfall for both electricity and heating here, and all this added up gives us the total of the energy cost without CHP and the energy cost with CHP. Of course, the night period is neglected because the CHP will not be in operation, so the savings will just be for the daytime period. Adding them all up together for each month gives us annual savings of just under 60,000. Now moving on to the overall findings from using each system, we can see here the electricity generated from the system and the heat recovered for running for the whole year period. We can see that the system size for the average demand is producing a lot more electricity, but less heat is recovered as the heat to power ratio of this system is lower. Here shows the maintenance cost related to each system. We can see here the energy costs of running each system and the savings. We can see here that the system based to deliver our base electrical demand is giving us a higher annual savings. See here the simple payback, 3.4 years using the Energy at 230 system, and 4.1 years using the 310 system, which is sized to the average demand. Again, we can see the savings in emissions. This system offers a lot more electrical savings as it's producing more electricity, and there's more CO2 emissions related to generation of electricity than heat. Now, a thermodynamic analysis was carried out on both systems, just showing here the efficiencies and the losses associated with the system. This here is for the ENERG 230. You can see there's loss related to the generator, exhaust, as all the exhaust heat cannot be captured by the heat exchanger, and there's a radiation loss of about 3% from the whole system. This gives the system an efficiency of 90.6%. As we can see here, the electrical efficiency 35%, thermal efficiency 55%. Again, some of the parameters just going through your fuel input, your output, electricity output heat, and some other calculations. Now, the conclusion. From it, we can see that the hospital is feasible for the use of two systems were analysed. We can see that substantial savings were made with both, with the system based to the base electrical demand of the hospital offering the most savings. So this was the ENERG 230. So we would recommend the installation of this unit to the hospital, and it will save them a substantial amount of money on their energy bills. Now, thanks for taking the time out to watch this video, and we hope you enjoyed it.